just shorter. Thank you very much. It's a great pleasure to participate in this GDR and to be back at IHES. GDR, was it the last time I was there? When Kirchberg and Wasserman were speaking, was that GDR at the CIRM? No, or it was not?
Perhaps.
I think it was. I think it was. Anyway, that's a long time ago. Okay, so thank you for coming. Thank you for coming so early. And so let me start right away with the heart of the problem. Local to global means that I'm interested in a conjecture of Eberhard Kirchberg in his very remarkable paper from 1993 in Invenciones. He asks whether the local lifting property implies the lifting property in the separable case. So it will be always separable C-star algebras. And by the way, it's only the separable case because if you look at this quotient, L infinity over C0, it's well known that there is no bounded lifting. So, you know, even in the commutative case, non-separable, you have counterexamples to lifting. And it's only separable case that can give some interesting results. So we'll stay in the separable case. And I will define, of course, what's local lifting and what's lifting for the talk and for Kirchberg's paper. The partial motivation for me, it was a big motivation, was that this is related somehow to the Kohn-embedding problem. Because as asserted in Kirchberg's paper, the Kohn-embedding problem is equivalent to the fact that the full C-star algebra of a free group with, say, infinitely many generators has the weak expectation property. And this implies that the local lifting implies the global lifting. So if you believe the Kohn-embedding problem, then it should be true that local lifting implies lifting. Now, the situation is complicated because there is, as you all know, a preprint that was, you know, posted on arXiv 2 years ago that apparently has not been completely checked, but, you know, there's at the same time no reason to doubt because it's been 2 years and no, you know, big obstruction has been found. But the proofs use how to say, let's say, computer science, ideas from quantum information theory, quantum games, and so it's very difficult to check for someone not familiar with these areas, and so it explains this huge delay. The preprint is by G. Natarajan, Vidic, Wright, and Yuen. Okay, so for this problem, I can describe the situation. It's very negative, as I have 2 lines of attack, and both I'm stalled, I'm stuck in both lines. And just for, you know, provocation, one project would be the following. I forgot my first line on this slide, which is that the hope that I have is that recently I've been able to construct a C-star algebra, which is, I can say, a new example of C-star algebra with local lifting property. And this C-star algebra is constructed very much by local methods, local meaning everywhere, finite dimensional. So it's a finite dimensional, an inductive limit of finite dimensional spaces. And I hope, I can even, you know, sort of, well, I have been wrong many times. I can dare to conjecture that this example fails the lifting property. And if it can be shown that it fails the lifting property, then this will not be easy because it will show that the Kohn-embedding problem has a negative solution. But another possibility is to show that if this algebra has the lifting property, then the Kohn-embedding, you know, the Kohn-embedding would be true. So I could rely on the preprint by the 5 authors to get a solution to the question of Kirchberg also. That's another possibility. So, you know, there are multiple routes that are, you know, the ambition is not the same in both projects. And then the other possibility is simply that, you know, well, I'm wrong, and this algebra has, it can be shown that maybe a variation has the lifting property. Then it's a very interesting example that's even stronger than the preceding one, with global lifting, weak expectation property, and so on. Okay, so I hope to get in the end to have still 10 or 15 minutes, it's optimistic, for showing you more details, and then I'll go to the blackboard. But first, let me explain what goes on, what are the terms of the problem, and so on. So lifting property, of course it's lifting for this. It's associated to this diagram. We have a quotient C-star algebra, and we have a map U from a C-star algebra A into a quotient. I'll keep the notations all the time. Okay, same notations all the time. So that should be easier to follow. And we want to lift. So the lifting is U hat. And lifting and local lifting, in both cases, we have U unital completely positive, let's say. So let's take the unital case, unital completely positive, and we want to lift into unital completely positive. Now, for the local lifting property, what is local is that instead of trying to lift the whole U defined on A, we restrict U to an arbitrary finite dimensional subspace. That's the danger of this pointer. We restrict U to a finite dimensional subspace, and we try to lift only the restriction to E. So that will be a finite dimensional, say, operator system, and we ask for this lifting, which now depends on E, to be also unital completely positive. So that's the local lifting property in the sense of Kirchberg. Now, the examples of C-star algebras with lifting property, it's a little bit strange, are two types. One is nuclear C-star algebras, and this goes back to a paper by Choi F. Ross in 1977, a very well-known paper. So C-star G for G, amenable countable discrete group. And on the other hand, quite different example, full C-star algebra of any free group, say Fn, non-commutative free group, so with two or infinitely many generators. Usually I just take infinitely many generators. So both have the lifting property. The second one was proved by Kirchberg, and the proof is not so easy. And part of what I'm presenting here actually produces another approach, another proof of that. So we could say that a discrete group has lifting property. The discrete group has LP. If the full C-star algebra of G has the LP, and then you see that there is a strange class of groups, amenable groups and free groups, the union of these classes, that are included in the lifting property. So well, you could say first it's not clear how to really get a characterization of groups with this property. Not even clear what could be conjectured, or at least not clear to me. And to give you an idea of the state of things, well, it's open whether just the product of two free groups has the lifting property.
Est-ce que c'est connu pour les groupes hyperboliques?
Non, je crois pas.
Parce que F2 croix F2 n'est pas hyperbolique, et les groupes libres le sont, etc. Ce serait naturel de regarder.
Oui, peut-être, mais non, on ne sait pas. C'est vraiment très peu de choses, très peu de choses. Ok, donc voilà. Maintenant. Attends, je t'ai fait switcher au français. Là, il faut que tu... Ah, c'est vrai, exact. Sorry. So, okay, so if you have this class, then the very naive way to say, well, if it's not amenable, then we look at free groups. Free groups have also the property. So actually, it's not easy at all to find counterexamples, to find groups, which fail the lifting property. It's surprising. It has not been easy. All the examples that have been found are examples with Kazhdan property T, starting with Ozawa, who showed existence, some group, but inside some, inside some continuous collection by some sort of combinatorial argument, and rather complicated, it was proved that there exists some group. Andreas Thom managed to find an explicit example, and recently, well, things were really settled better because the usual groups with property T, SL and Z, were proved by Johanna Spass and Wiersma to fail the local lifting property. And a natural question would be just take a group with property T, you know, and of course infinite, and does it, you know, contradict this lifting property? Can you find an obstruction?
If it was true for hyperbolic groups, there are hyperbolic groups which have property T, so this would kind of...
Yes, okay, okay, so maybe, yeah, right. Okay, maybe that's the direction to go. Okay, one thing I'd like to point out, which I think is important to understand this problem whether local implies global. It's something that comes out of what I call, I think it's really the right way to call it, I call it Arveson's principle, and I state it as a principle, so you know, as a general fact, and as a principle something you can remember, which is it's a surprising fact actually. Pointwise limits of liftables are liftables. So if you just have pointwise limits of maps which, you know, admit good lifting, so F is some class of maps, you know, for which you can study the lifting problem, script F, so take unital completely positive maps. But it's a principle, so it's valid actually for many other classes. You can write exactly what you need for that. But so it's a very general principle. And it tells you that, and here it has the following consequence. So we're interested in knowing that we have lifting property starting from local lifting, right? This is our problem. So look at the diagram. Just we erase this one. We still have here a commutative diagram, okay? And now assume that this extension UE. This lifting, sorry, UE, admits an extension to A. So, you know, that's the most natural approach because we are looking for a global lifting. But it's just an extension of the restriction, you know. So of course, outside of V, that doesn't tell you that it's lifting of U, okay? You're only lifting the restriction and then you're extending. Okay, but if you can do this in such a way that this map, capital UE, is still in the good class, unital completely positive maps, then you're in business because you see QUE as a net indexed by the finite dimensional E's, okay, which you view as tending to A. This will be such that QUE tends to U, because when E is large, you know, your QUE coincides with the original. So definitely you have this limit. And so it tells you that you can patch things. That's the content of the principle. And the map is liftable. So what is amusing, which I like to emphasize, is that you get that the problem to pass from local lifting to global lifting is closely related to an extension property. And this is not so natural that lifting is the same as extension. And you know, in fact, when one says that, you probably are blinking at, sort of, you know, frowning, because of course, by duality, if I look at a diagram of lifting and I transpose everything, I get an extension, you know, diagram and the problem of extension. But we are not transposing. It is the same diagram on which we are asking for a certain extension. Okay, so I use a terminology that's very convenient. I call a nuclear pair of C-star algebras, a pair of C-star algebras on which there is a unique C-star norm, so a unique tensor product. The min and max norms are equivalent, are equal on the algebraic tensor product. For me, A tensor B is always the algebraic tensor product if it appears. Okay, and by the way, we are dealing with C-star algebras, so if the norms, these are C-star norms, if they are equivalent, they're automatically equal, because another principle says that on a C-star algebra, after completion, there's a unique C-star norm. So, once you complete, if they are equivalent, they must be equal. Okay, you all know, of course, what's a nuclear C-star algebra. So A is nuclear if the pair AB is nuclear for any B. And of course, I can reverse things. AB, BA, this is the same because for min and max, the tensor products are the same. I'm sure you all know also that nuclear examples are commutative C-star algebras, compact operators on Hilbert space, C-star G for amenable G, and Kunz algebras, while the standard counterexamples to nuclear would be C-star G for non-amenable G, the algebra script C, this is the case of the free group. I think I have my notation is coming. And this B is B of H, B of L2, say, for separable Hilbert space. So the pair that I call the fundamental pair, this is from Kirchberg's work, is the pair formed by B of L2, which I prefer to abbreviate by script B, and script C, which is this C-star algebra of F infinity, which I consider as really two fundamental C-star algebras. I'll amplify that in a second. So for me, that's the fundamental pair, and it's a rather striking fact that when you look at this pair, it is a nuclear pair. Okay? Even though each of the two algebras, C and B, individually is not nuclear. So one of the things I'm actually very proud of is that the proof of Kirchberg is rather hard to follow, and I gave a very simple proof in a paper in Journal of Operator Theory in 1996 based on a linearization trick that has proved very useful. Why fundamental? Well, first they are universal objects because any separable C-star algebra is a quotient of script C. And any separable C-star algebra embeds in script B, okay? So it's either universal for quotients or universal for embeddings. And moreover, B is well known to be injective, right? It's an injective object in the category of C-star algebra. And C, in some sense, is projective because we already said it has the lifting property. So if you think like in Banach spaces where I come from, it's very natural. C looks like L1 and B looks like L infinity. But to say that C looks like L1 is kind of something difficult to argue, really. You have to be, well, it's very vague, very vague. Okay. So Kirchberg's characterization of the local lifting property, and I'm going to use every time characterization using tensor products. That's why I reminded you what they are here on this board. So a C-star algebra has the local lifting property, which we have defined before, if and only if simply the pair AB, B of H, is a nuclear pair. So explicitly, this means this line here. And a variant which is good to know is that we could replace B of L2. There's no difference for this property of being a nuclear pair. B of L2 is really equivalent for this property with the algebra boldface B, which is the direct sum in the sense of L infinity, this is the notation that I use for that, of the family Mn indexed by n, that is all matrix algebras with all possible dimensions. Okay, which in the C-star literature they denote by products of Mn, which has always bothered me, but okay, that's life. Okay, so of course now you see as a corollary, it's not that it's an important corollary, it's just to see it fitting in the picture. C has the LLP because the fundamental pair tells you that CB is nuclear. And now we are saying that an algebra has LLP if and only if paired with B it is nuclear. So C is an example, right? C has the LLP. This is encoded in this statement. Okay, stability properties, I don't want to spend much time. It's stable by the obvious operation when it's defined by this tensor product. So it's stable by extension, by finite direct sums, by maximal free products of arbitrary families. And another property which is more interesting is that you can consider the property that the identity of A factors through a C star algebra C. So the diagram is here. Identity of A is factored through C with maps U and V that I assume decomposable. So decomposable, that means linear combination of completely positive maps. Okay, and I will explain in a short while why this makes a difference to be like that. But anyway, here, when you have such a factorization, then you find that the property of C will be inherited by A. Property being lifting property or local lifting property. So if C has one of these good properties, A inherits them from this factorization. One could make it a little better by making it local and so on, but I try to keep it simple. One result of stability that I like to insist on is that the local lifting property is stable under closure of unions of, increasing nested families, like there, right, in the usual ways. So if all the AIs have local lifting, then A, this inductive limit, will have the local lifting. And this is easy to see by the tensor product characterization. It's just a couple of lines, it's an exercise. But I've noticed that I have no argument, so it is easy using this, but I have no argument for the lifting property. So the same thing with the lifting property, it's considered in Kirchberg's paper, but he needs to assume that the tower of algebras is special, that each one is somehow complemented in the next, and it's a very trivial situation. And it should be true, because we are claiming that local lifting is the same as lifting, right? Of course, lifting is more general, so of course, lifting implies local lifting. Okay, so the analog is unclear for lifting property, and I like to insist because I think that's an open door also for a construction of a counterexample, which of course I have played with so far with no success. Okay, so I should tell you a few facts about tensorization of linear maps, but hopefully you already know this. So, Mn of A can be identified with the minimal tensor products of Mn and A. And if Un denotes this map, the map U extended somehow to the matrix level, the CB norm is usually defined like this. And from this definition, one immediately gets that if you have a tensor product of two maps, which are each one completely bounded, then the tensor product will be completely bounded on the minimal tensor products of the first ones to minimal tensor products of the other ones. And this statement does not extend to the max. For the max, it is not true. It is a very important observation, a very fundamental one. So for the max, what works is completely positive maps. So completely positive maps will tensorize, and more generally, linear combinations of completely positive will tensorize, because your linear combination will be linear combination of four maps, right? Because you will always have, positive minus positive plus I times positive minus positive. So just like for signed measures, complex measures. So the decomposable maps from A to B are this set, and if U1, U2 are decomposable, then your tensor product will be bounded and, in fact, decomposable also. Okay, completely positive maps have the norm equal to the deck norm. And if U is self-adjoint, the deck norm, this is something that Hagerup found, which has proved very, very useful, Hagerup in the 80s. The deck norm can be defined for the self-adjoint case like this. That's a fairly natural definition. Inf of this over all U decompose as U1 minus U2, U1, U2 completely positive. Incidentally, I don't know if there is something in the literature on lack of uniqueness. I said it's like measures. For measures, you have mu plus minus mu minus. And I don't know if somebody knows papers worrying about counterexamples. I suppose there are counterexamples, but I haven't seen anything. Okay, and I mentioned that Hagerup, you know, had contributed something on the norm. So he had this smart idea to actually go to this 2x2 trick to define the general, the decomposable norm of a general map, not necessarily self-adjoint, by reducing it to the self-adjoint case. So this was for self-adjoint. So that's analogous to real measures. And now there's no measures. That's really not commutative. That's this trick here that gives a good way to define the norm, which, you know, harmonizes the results. So in particular, it harmonizes this. It gives you that the tensor products of two deck norm gives you a bounded operator of two deck maps, gives you a bounded operator on the max tensor products, between the max tensor products. And I could add here deck if I wanted, but like this. Okay, and the deck norm, of course, the deck norm is stronger than the CB norm, which is obviously stronger than the original, the original usual norm. Okay, so one result that I proved recently and that I was hoping very much to use for my project, which I told you is not conclusive yet, is that I managed to find a characterization of the lifting property that is in terms of tensor product in a very, very somehow nice way, very, you know, sort of neat way, say, which is indicated here as star. And it's a sort of a commutation property between the maximal tensor product and direct sums in the sense of L infinity for an arbitrary family di of C-star algebras. So the property means that this is isometric. So what it means is that, if you like, on the algebraic tensor product, since what I'm pointing out now is the completion of the algebraic, okay? So what this is saying is, on the algebraic, so just finite rank tensors, the norm corresponding to this, following, you know, this rule here, is exactly equal to the soup of the norms of each coordinates. You have a natural, you know, fiber coordinate here for this tensor product, which is just formally a trivial algebraic correspondence. So you have here on the right the soup of the max norms, and on the left you have something which is, you cannot say more than saying that it comes from, you know, the definition of the max tensor product. And the property that these match, that these two things are actually equal, is exactly the same as the lifting property. That's the content of the paper, which is to appear in the Journal of Non-Commutative Geometry. Maybe this is why I was invited. Okay, that's probably a joke. Three important remarks here. First, this looks complicated, but in fact it's very easy to simplify it radically by first taking just sequences, because, you know, we reduce to, well, separable subalgebras suitably and so on. And we can reduce to each C-star algebra being a copy of the algebra script C, which is my notation for C-star of F infinity. Why? Because everything, all these di's are quotients of this algebra. They are quotients of this algebra. And the max tensor product, this is something that maybe I should have written on the board. The max tensor product has a projective property. It has projective properties that the min tensor product fail. The min tensor product is injective. That's actually its other name. It has injective properties. The max doesn't have injective properties, but it has projective properties, which means it behaves well with respect to quotients. And so that's the reason why one gets this nice simplification that, you know, if everything is a quotient of this guy, script C, we can concentrate on that with respect to such, you know, properties such as this one. The other thing to remark is that, of course, this property here star, if you replace max by min, then it's always true. This is, you know, this is clear. This is the obvious remark that the norm of an operator, you know that the minimal norm is just the norm of the operator acting naturally between the tensor products. And the norm of an operator, when it is block diagonal, when the operator is block diagonal, the norm of the operator is the soup of the norms of the blocks, right? We use this all the time. So for the min, this is exactly what this expresses for the min, and it's a true fact. Okay. So lastly, in the case of the algebra A equal to script C, so now this A now is equal to script C, how to check this? It's good that I have a way to do this, and I can do this, I claim, by linearization trick, the same linearization trick that I used for the local lifting. I can use it again here, and that's good for me because that allows me to claim that then the proof that star implies lifting property that I have in the paper includes the algebra script C. That is, without using, I'm not using the fact that this fundamental algebra has lifting property, I'm reproving it in this theorem. So that's why I can claim that I have a second proof or a second approach to that theorem. Okay, so a good way to illustrate, you know, how things fall into place is to show you actually a weaker fact. Just check. Let's check that star implies local lifting property. Okay, and anyway, they're close. So let's look at this. So that's an exercise. So star is this thing. Okay. Now let's look at di to be the collection of the mn's. Then that means exactly this: L infinity of mn tensor max is isometrically, canonically embedded in L infinity of mn tensor max, but mn is nuclear. So each mn is nuclear. So mn tensor max is the same as mn, is identical to mn tensor min A. So we have that this is inside, isometrically inside that, which is this line here. Okay, so now I put it like this because we're on the left, we're always completing the algebraic tensor product. And so this is just saying that, you know, the norms match. But on the right, I can claim that I still have the completion of the algebraic tensor product for the norm which is here. But the norm which is here turns out to be the same as this one because of this block diagonal argument that I just told you, that for the min it is clearly the same. Okay, so we get this. That means we get this identity for the algebra B, which is the L infinity direct sum of the family Mn's. And so that's Kirchberg's characterization of local lifting property. So that's the hierarchy of how to go from star, which is the same as LP, to local lifting. Okay, so the main tool that I use to prove this theorem on the characterization of the lifting property is something just very natural, but which has turned out to be very fruitful. I look at the analog of completely bounded maps simply for the max tensor product. So when I have a map U from an operator space E sitting in a C-star algebra, and this is important because we cannot forget where it is sitting. Okay, so it is sitting inside a C-star algebra A. We cannot forget it because this is used in order to define the max tensor product of another C-star algebra D and E. We use the embedding of E in A, and we simply induce the max norm of D tensor A on D tensor E, and we complete. But if there was a larger algebra than A, you know, like for instance B of H or something, and if we do the same thing, we'll get a different result. It's clear we'll get a different result in some situations. So that's important. We need to remember that there is an abuse. It's an abuse of notation, but quite convenient somehow to see the parallel with completely bounded. So the definition of maximally bounded, and I put MB as the index, is that just when you tensorize with an arbitrary C-star algebra and look at the max tensor product, you preserve boundedness. So again, if you put min here, oh, something is missing. Yeah, something is missing. Yeah, I think I tried to compactify too much. So the definition of the MB norm is the soup over all D. Okay, is the soup over all D, right? It's the soup over all D. Or if you just use 1, you can use C and observe that everybody being a quotient of script C, then that's okay. You can just use 1 script C. Just like for completely bounded, you can just use B of H because they contain everything. Okay, and so, you know, we have a Banach space of maps, MBEC. And something similar can be done for completely positive, so that would be maximally positive for an operator system, but I have very little really use for it. It just works nicely, but not much. So one key tool to prove this theorem characterization of lifting property is this. It's an extension theorem for maximally bounded maps. And the best is to look at the diagram, okay? To look at the diagram and the formula. Look at the formula and look at the diagram. And so it just says that when you have a maximally bounded map U, you can extend it and preserve the maximally bounded norm, maybe up to some epsilon. But you have to extend the range to the bidual of the range. So you look at the inclusion of C into its bidual, and if you enlarge in this way, then you can extend. So that's nice because that also has, of course, the analog, you know, the analogous fact for the min corresponds to something that will come next, injectivity or weak expectation. Okay. So here just a few facts. So Kirchberg proved that when you're defined on the whole of A, and I use his arguments for this result, when you're defined on the whole of A, then the MB norm of U is the same as the deck norm of ICU, that is the deck norm of U with the range enlarged to be the bidual. Also, this corresponds to something that's been already said. The maximally bounded is less than the decomposable norm because I've told you that the deck norms tensorize well with the max tensor product. So that statement implies, you know, or means this fact here. And if C is a von Neumann algebra, you see these biduals, of course, when C is a von Neumann algebra, things will fit very, you know, nicely into the bidual, and so it's the same thing as the deck norm. So when C is a von Neumann algebra, when C is a dual, this is the same. Okay, so this is like a recapitulation. So, you know, we have this statement here. And I've now written star just with the family that is the family of all di's equal to script C. Let me show you a sketch of how we get to star implying the lifting property. So it's convenient for me for what I want to say in the last part of the talk, so I naturally introduced introduced one more norm, so it's beginning to be perhaps too much, but anyway, and it's not the last one. I introduced this norm SMB, which is for a map U from E to a C-star algebra C, this norm. So we tensorize. E is finite dimensional. Okay, so that's just to avoid complications. So E is finite dimensional. So we're always here. This guy here is really the algebraic tensor product of E and L infinity C. Okay, so on this algebraic tensor product, we have this norm. We apply U, and we ask that it is bounded with on the target space with respect to the max tensor product with L infinity C. Okay, so the property star with this notation just means that for any E finite dimensional, the identity of E is like that, okay? Because that's exactly the content of property star. And then for any map U from E to C by composition, it will be the same as the SMB norm will be the same as the MB norm, because this MB norm controls the max, works well with the max, so that's good. So the key fact is which I observed is that there is a local reflexivity principle for norms that are defined like this, or for, if you like, mapping spaces, okay, of this type. And I have actually I can write sort of a condition that works. It is related to what happens on this domain here. So anyway, what it says is that this natural, this mapping, which is really an identification, because E being finite dimensional, the two spaces on the left and on the right are the same space, but this cryptic notation means that this is included with norm 1. Okay, so the unit ball on the left is included in the unit ball on the right. I just wanted to sort of compactify in the slide. That's what such local reflexivity principles usually mean. Okay, so to prove that star implies LP, we already did one step. We showed that it implies local lifting property, modulo, all the previous results. So we are back to our extension problem. And so now I will just sketch that there is an extension lemma which exactly gives us what we need. And the extension lemma that is needed, I showed you the diagram earlier, is that certainly it will be enough for us to be able to extend a map U from E to C to a map from A to C, preserving this MB norm. Okay? So anyway, that's the thing that works with this extension problem that I have explained as critical for passage from local to global. Okay, and so if you use the fact that A is separable, and you exhaust the space A using, finite dimensional subspaces E here, E1, that contain E, you are left with the problem to extend U from E to C by a map on a larger finite dimensional space, and with the control of the MB norm like this. So if you can pass just from E to a larger space and extend and control the norms, that's enough. Your space is separable. It's a well-known argument. And so that's where the local reflexivity fact becomes crucial, because when you let's see, when you have property star, you see when you have property star, this thing that I've denoted SMB is the same as MB, because we're inside the algebra A that has the lifting property. So the key is that this algebra has this commutation between L infinity direct sum and max tensor product. So because A has this property, it gives us that actually we have a local reflexivity principle for MB simply. Forget the L infinity. Okay, and now, that's a standard argument. Now, if you have a map from E1 to the bidual, and we know we can extend into the bidual, because I told you that, we have this extension of MB maps when we enlarge the range to the bidual. So we have the extension into the bidual, and this local reflexivity tells us that our map, which is in the unit ball of this guy, is the pointwise limit of a net of maps in the unit ball of maps from E1 to C. And when you're dealing with an extension problem like that, well, I don't know if there is more. No, sorry, there is not more detail. So then there is a, then I want to stop the argument just for those of you who know this argument. So then Mazur's theorem comes up. Mazur's theorem is this famous theorem that says norm closure of bounded convex set is the same as weak closure for the weak topology. And here the bidual, since the maps are into C and we look at the weak star topology, on C that's the weak topology, right? when we are on C, the weak star topology of the bidual is the weak topology. That's this content of this trick. And then convex hull of the maps gives you norm limits, and you get the extension. Okay. Now about the weak expectation property. So the weak expectation property of length, just without going through lots of variation, says that C-star algebra has WEP. Same thing, it's good to look just at the diagram. When your algebra is viewed as embedded in B of H, you can say it has the WEP simply if the inclusion into the bidual admits a map which at first reading you could say it looks like a projection. So it's a map from B of H to the bidual, which is the identity on A. T of A is equal to A for any A in A. So T restricted to A is the identity. But that doesn't make it a projection, and that's a map which is, so this map which is here required to be completely positive and contractive, and then there are lots of results. You could just say contractive, it will then be automatically the other properties and so on. But let's say it's contractive, completely positive, and it makes this diagram commutative. So this map T is called a weak expectation, and that's the origin of the name weak expectation property. It's good to know that if you look at the diagram and you introduce the extension of this map T on the bidual of B of H with values in still the bidual of A, so this map is the canonical normal extension of this map T, so it will still be completely positive contractive, and now that's a projection, that's a good old projection from the bidual of B of H to A double dual. So that way to look at things puts it very well in analogy with injectivity, injectivity being the case when you have a phenomenon algebra or a C-star algebra like this, but complemented by a projection of norm 1 in B of H, not its bidual. And by the way, I cannot resist really saying that, but if you now look, if you ask yourself, oh, there is an interesting property here, which would be, let's say that we forget the diagram on the left, and we say that we have a C-star algebra A, and we look at the property, it is embedded in the bidual of B of H, okay, the bidual of B of H, and there is a projection, even it could be normal, here it's a normal projection. So a normal projection of norm 1 unital completely positive. Suppose you look at this property. One of Kirchberg's conjecture is every C-star algebra satisfies this, and that's equivalent, according to Kirchberg, to Cohn's embedding problem. So one has to be careful here that this arrow here is the bitranspose of this map. And then the statement expresses the weak expectation property. But if you don't say that it's the bitranspose, then actually there's no counterexample known, except in 5 author preprint by means of consequence. Okay, so we've already proved that A is local lifting if AB is nuclear. So another theorem of Kirchberg is the characterization of the weak expectation property by the fact that the pair AC is nuclear, where C is this script C, full C-star algebra of the free group. And moreover, the generalized form of Kirchberg's theorem, which he had in his paper, of course, is that, I write it in a provocative way, WEP LLP is nuclear, meaning any WEP you can put, any LLP, you will get a pair that's a nuclear pair. Okay? And in fact, another way to emphasize is B is LLP if and only if you get a nuclear pair whenever you pair it with a WEP, and A is WEP whenever you get nuclear, whenever you pair it with an LLP. So there is a sort of like a duality, principle, which okay, which is beautiful, but well, it's that's no. Yeah. Okay, so what is this example that I was telling you about earlier? So Kirchberg proved, as I just said, WEP LLP gives you nuclear pairs. So if a single C-star algebra is both WEP and LLP, this theorem tells you that we will have the minimal and maximal tensor products coincide for A tensor A. And in fact, I could just pass to the opposite algebra because these properties, weak expectation, local lifting, they are invariant. They pass to the opposite just as well. Or we could have A up, tensor A up, or there are variations one could do. And so what we need to recall, to record, is that if A is both WEP and LLP, then we have this identity. And Kirchberg, in his Invenciones paper, produced the first example of a C-star algebra with this property. It was a long-standing open question raised by Lance from the beginning, and it's motivated. The question was whether, sorry, I'm not saying this well. The question was whether you could have such a C-star algebra without being nuclear. And it's a natural, if you think of it, that was a natural question to ask, because there is if A is equipped with a tracial state, you immediately have an action of A by left multiplication on the L2 of the trace, and an action of A by right multiplication. The right action is a representation of the opposite C-star algebra, as of course you know. So there are very immediately natural star homomorphisms on this pair, while for others it's not clear. So it was actually believed, I think, that this would be true, and Kirchberg showed that it is not true. Now my example is different because I have this separated properties, and the local lifting property was missing in Kirchberg's example. Anyway, apparently it seems. So it's a inductive limit. The particularity is that it's an inductive limit not of C-star algebras, but of finite dimensional subspaces of the cone algebra over C. So, and another board here planned. So the cone algebra over C is here. That's the tensor product of continuous functions on the semi-open interval 0, 1, and C. And this is just to have some sort of idea. So the inductive limit it's important, is done so that the spaces ENs are what am I writing? Yes, so are embedded almost isometrically one into the next. So this here these norms tend to 1. We have a certain degree of multiplicativity. So here the product of two elements was like that. I'm forgetting that also they are self-adjoint maps. And TNs are asymptotically multiplicative. So this is just to give you an idea that if you construct such an object, you can actually get a C-star algebra. One can check that this will produce a C-star algebra. And if one works with these maps and proves uniform estimates of these maps by an inductive construction, one can get the WEP. One can get the WEP, and then one gets also that, A locally embeds in script C, and also that C locally embeds in A, and from these properties, the local lifting property follow. Here I'm really sticking things under the carpet. I'm not giving you proper details. So my conjecture is that A, this example, or a variant of it, might fail the LP, but I couldn't prove it. And what I have is this theorem. So it's I don't know how you could say this is a fake theorem, or this is a phantom theorem, or something like that, because it proves the equivalence of properties which I can't decide whether they're all true or they're all false. But I hope you'll agree that there is still some content in such a theorem. After all, Kirchberg was doing the same thing, if you look at his paper in Invenciones. So I'm following his example here. So it's the following. So if it's equivalent, I could check this, it's equivalent to have that one of the examples that I just described has the lifting property. And then if one of the examples has the lifting property, the examples that have the property that C locally embeds in the example, and local embeddings is defined here. So because it's an example that's sufficiently rich, it's not, you know, the ideal thing would be that it's isomorphic to C. Then, you know, we're finished. We've proved positively the cone-embedding problem. But we cannot prove that it's isomorphic to C. We only claim that it looks locally like C. Okay, so from the fact that it looks locally like C, if it has the lifting property, then we get that lifting property, local lifting, implies global lifting for any C-star algebra just with weak expectation property. So that example at least controls, you know, the whole class of WEP algebras for our problem. And then a strange thing appears, which is that the inclusion map, so you could take the inclusion map from this C-star algebra script C into B of H. So, you know, any C-star algebra, any separable C-star algebra embeds in B of H. So this J exists, there's an injective star homomorphism, an isometric star homomorphism that embeds this C in B of H. And then the property is equivalent to a property of this single map or any other map or any actually completely isometric map like J. It should have the property that it makes you pass from the min to max when you tensorize with L infinity of C. And I was very bothered when I got to this point. I was really hopeful that that I could, you know, show that this is not true, or anyway decide. You know, I cannot decide. This is the problem, whether it's true or false. And for the next one, it's even more infuriating, because the next statement says that there is a completely isometric embedding of script C into C, such that the min and max norm coincide on the range of this embedding. And so, of course, if this F was onto, here again, you would have C tensor C min equals C tensor C max, and therefore you would have the cone embedding problem. But so again, when I stepped on this, I was hopeful that, you know, oh, now I'm going to be able to conclude. Well, I couldn't conclude that this implies the cone embedding. And now the very embarrassing thing is that I could not conclude even if this F is a star homomorphism. And so I'm asking you here for help, because I feel very silly that, you know, this looks like incredible, but I can't see an argument if just F is a star homomorphism, not surjective and, you know, isometric. I cannot see that it implies the conjecture. I think I'm through, but let's just finish by advertising my book on the question. Thank you very much.
Thank you very much. So are there questions or comments?
J'ai déjà posé ma question sur les groupes hyperboliques. Parce que justement, les groupes hyperboliques ont cette propriété qu'ils peuvent avoir la propriété T tout en étant très proches des groupes libres. Donc ils sont juste à la limite. Et ils ont cette propriété justement que ils sont plutôt de rang 1, c'est-à-dire dès que tu fais un produit de 2, ça marche plus. Donc, bon.
J'ai pas regardé, à vrai dire, mais je pense que Ozawa a certainement regardé, donc je ne sais pas, je ne me suis pas précipité sur ça. Je suis sûr qu'il a regardé ça.
Any other question, comments?
Non, mais donc là, à la fin, là, quand tu parles des groupes libres, de C, etc., on a vraiment l'impression, effectivement, d'être très proche de ce qu'on regardait. C'était exactement ça.
Oui, oui, oui. Non, alors c'est justement, bon, je suis à peu près sûr que oui, bon, on va creuser, puis on va arriver à revenir en arrière. Ah, enfin, à moins, après tout, à moins que, je sais pas, mais oui, probablement on va revenir en arrière au sens démontrer effectivement que ça implique ton problème, et donc ça dépendra de la solution du problème. Ce qui est évidemment pour moi une grande déception. Bien entendu, j'aurais préféré faire directement, mais enfin, ce serait déjà ça. Oui, ce serait déjà ça. Et par ailleurs, j'ai oublié de dire qu'il y a un autre vieux problème, encore plus vieux, qui moi me fascine, qui est un problème qui peut être qualifié de local implique. Sorry. Yes, there's another big problem. I'm asking myself a question. This is okay, sort of. Yes, which is simply that we've looked at local lifting and global lifting. Suppose now you say, okay, we forget unital completely positive. Suppose we say contractions, or just bounded linear operators, okay? Then, so let's say for contractions, local lifting always holds. This holds. It's a consequence of combining these ideas, Arveson's principle, Banach space local reflexivity principle. It gives you, it works locally. Global is open. Global lifting with contractions for separable C-star algebras is an open question that goes back to the early 70s, work by T.B. Anderson, Westerström, and Ando. And they were working with a quite different language, faces, split faces, and so on. Probably you remember that. There were lots of talks in conferences in the early 70s about that, and then problem disappeared from circulation. I'm pushing it every time because I think it should be answered. But it's kind of maybe more a Banach space problem than a C-star algebra problem.
I actually have a question regarding this link with the cone-embedding problem that you were mentioning. So no matter the outcome of the investigation on this preprint, I think the question of an explicit non-embeddable algebra is still very much open.
Yes.
And from what I understand from this local lifting to global lifting, there is also the question of can we find an explicit. Would there be a link in one way or another that one?
It's much more. It's the same type, but it's much more direct because you would have an example of a C-star algebra that's not QWEP, so at least that's the first step. And then you unravel. So if you unravel, you get the phenomenon algebra at the end. But the way I'm presenting things, indeed, if I could do what I did, I would not have it immediately ready, the explicit form.
And it's maybe very naive, but is there another way around? Like if we have a non-embeddable factor, is there a way to get a C-star algebra which doesn't have, which has local lifting but not global lifting?
Certainly, but I can't immediately answer, but maybe later today. But yeah, I'm pretty sure, yes.
Okay, well, let's thank Gilles again for the talk.